Hi everyone, welcome to Chapter 8. We're going to spend most of our time in this chapter talking about gases. We'll also talk about liquids and maybe solids briefly. So what do we mean by a gas? I think most of us have a pretty intuitive idea of the difference between a gas, a liquid, and solid, but to put it in a little more quantitative terms, gases have no definite shape. Basically, they can fill the container that they're put in. So the air in your room right now is just filling up the shapes of the four walls and the ceiling and the floor. But if you put it in, say, a 2 liter of pop, then it will just sort of fill up and take the shape of the 2 liter of pop. So gases have no definite shape. Liquids and solids, of course, have definite shapes. Solids typically don't change from day to day. Liquids, of course, take the shape of the container they're in as well. But when you pour them in there, they only go up to a certain level. But the one really cool thing about gases, though, is that they can be compressed. And if you breathe in and kind of purse your lips together and hold the air inside, you can just imagine me doing that right now. You can kind of push on your cheeks and you can squeeze the gas into a smaller volume. So that's one really neat thing that gases do that liquids and solids don't tend to do. So you might say, well, why study? So what's the point of studying this? Well, if you've been following the news, one major reason to study, of course, is respiration. The idea that you are constantly breathing in oxygen and you are breathing out oxygen in a depleted form, and carbon dioxide and water. So you're constantly breathing in oxygen gas, and you're constantly breathing out sort of the waste products, carbon dioxide and water vapor. So when you're dealing with gases, there are 4 physical quantities that we always talk about. So these are 4 things that we can measure and give numbers and units to. The first one is volume. So volume we measure in the lab all the time, right? And we normally give it the symbol V when we're dealing with volume. We also deal with temperature, and so those are things that we've measured in the lab too. We normally symbolize it with a capital T. The third thing that we did a lot in the stoichiometry chapter is the number of moles, or the chemical amount. The number of moles of a gas we normally symbolize with N, so think of N for number. And the fourth thing is pressure, so the pressure of a gas we normally symbolize using the symbol P. So we've got pressure and number of moles and volume and temperature. And so if we're dealing with gases, we want to know how those 4 things relate to each other. So let's chat about pressure. So what is pressure exactly? Pressure is defined by our physicist friends as it's the force per unit area. So you basically just take the force, which we can symbolize as F, and divide it by the area A. And so we can imagine, the air is a gas and it is pushing down with a force. And if we take that force that the air is pushing down and divide it by the area over which the air is experiencing that force, then we can calculate the pressure. And so we can instantly see, right, that the smaller the area is, the bigger the pressure is going to be. So imagine if you go ahead and you slap the person sitting next to you with their permission, and you do the flat of your hand. You apply a certain force over kind of a large area. It hurts a little bit, but if you take your hand and you turn it side on, and then you karate chop them, that's a much smaller area, so that gives rise to a much higher pressure. And of course, if you poke them with your finger now has a teeny tiny area, and so the same force divided by a tiny area gives rise to a large pressure. And of course, if you've ever used a hypodermic needle, that needle has a tiny area, and so it gives rise to a massive pressure. So what exactly is atmospheric pressure? Well, if you take a look at this picture here of the Earth, you can see that the atmosphere is sort of a several mile thick layer that coats the outside. And what actually gives rise to this air pressure is that at every point on the Earth, let me see if I can blow this up. Okay, that looks pretty good. We've got a several mile high mountain of air. And, I'm not very good at drawing these rectangles here, am I? So there we go. It looks something like that, I suppose. And so if you are down here, right, then you've got this mountain of air essentially weighing down on top of your head. And it turns out that this air is absolutely massive in terms of the pressure it causes. It turns out that the weight of the air, or the force, is about 14.7 pounds per every 1 square inch of your head. So imagine taking a 15-pound bag of potatoes and laying it over every square inch of your head. So if your head is, about 10 inches by 10 inches, and we pretend it is square. That means it's got an area of 100 inches squared. And if we multiply that pressure is about 15 pounds per square inch. You're talking about 1,500 pounds of pressure, so about 3/4 of a ton of pressure, I believe, on top of your head. So that's pretty amazing, right? So you are right now causing or holding up about 3/4 of a ton of air over top of your head. So it's absolutely massive. Now those units there, so pounds over square inches, we normally refer to as PSI. So we can say that's about 15 pounds per square inch. So right now, air pressure is about 15 pounds per square inch. And the question is, how do you measure this? How do you know how much force is hitting your head? And the answer is we're going to use something called a barometer. Here's a picture of Torricelli's barometer. And so what we have here is a giant crystalline dish filled with mercury. And we have a very, very long test tube, about 3 feet long, that has been filled with mercury and turned upside down. And so the top is actually completely sealed. So what we find is, well, maybe I should go ahead and draw that. So this is our tub of mercury. Mercury is Hg, and it's one of 2 liquid elements. The other one is bromine. And we can go ahead and take a giant test tube, and we can go ahead and fill it with mercury. And so we sort of lay it down in the trough horizontally, and then we let all the mercury go in there, and then we turn it up and hold it by the sealed end. And what's really cool actually is that mercury, you might think, completely stays in the tube, but it turns out that's not the case. Believe it or not, the mercury actually falls out of the tube and leaves a little space at the top, and that space at the top is a void or vacuum. So believe it or not, that is the absence of matter. Now, that was very, very controversial. It took about 50 years or so for us to really use the word vacuum and not be worried about being put to death by the church for saying such heretical things. The idea of the church at the time was God was everywhere, so you couldn't possibly have a space in the universe where there was nothing. But it turns out that we kind of made peace with the religious folks, and they're okay with us using vacuums now. What's really neat is that the way this works and the way this measures air pressure is that the air is exerting a pressure. So I'm going to write P for the pressure and air for air, of course. And it is pushing down on the mercury. And that force on the mercury kind of helps to squeeze it up the tube. And mercury is incredibly dense. Mercury is about 14 times more dense than water. So it turns out that as that mercury squeezes or is pushed up the tube, the mercury itself weighs so much that actually counterbalances that. And so the weight of the mercury pulls down and the air pressure pushes up. And it turns out that it can only support a certain height. And the bigger the air pressure is, the more the mercury gets squeezed up the tube. And the smaller the air pressure is, the less the mercury gets squeezed up the tube. And we measure that height typically in millimeters. We can use any units we like, but we can use it in millimeters. So this is height. So H, I'm very sorry, my handwriting's appalling, in millimeters. And we use this as a proxy for pressure. And so we talk about this pressure in millimeters of mercury. So millimeters, and the symbol for mercury is Hg. And on a normal day, what we find is that we have an air pressure, which we call an atmosphere. And 1 atmosphere is the equivalent of a mercury column that's 760 millimeters tall. And so 1 atmosphere is 760 millimeters of mercury. And if you've ever had your blood pressure taken, you know, you might have a pressure like 130 over 70. And those are actually millimeters of mercury. So 130 millimeters of mercury when your heart is pumping, and 70 millimeters of mercury when it is resting. So those are the pressures above 1 atmosphere, it turns out. Now, because Torricelli, who was a student at Galileo, invented this barometer, we sometimes call, and actually in healthcare it's quite typical to call this unit the torr. In scientific terms, we often use atmosphere as ATM, but we can always convert between them if we want to. These are all exact, by the way. So an atmosphere is 760 millimeters of mercury. That's 760 torr for Torricelli. And if we use the SI unit of pressure, it is 101,325 Pascal. So Pascal is the SI, the preferred unit for pressure. Although quite frankly, outside of sort of physics land, it's really not used as often as the millimeter of mercury, the torr, or the atmosphere.